results I obtained in my PhD research. Just some of them, because there are too many. But what I did basically was a study that was divided in two main areas: a mathematical study of astronomical constraints of round-trip missions, in particular for Mars missions, and a system engineering study, in which we selected one particular mission, and we developed some system engineering or critical aspects of such a mission. You can see in that plot that I show you right up front, but I'll come back to it later, just to show you that there is a step reduction. This is a plot of time versus round-trip delta V for a Mars round-trip mission, where delta V is a heliocentric delta V. You can see that for a certain interval of delta V, if we increase the delta V available for the mission, the total round-trip time doesn't change. For example, if we go from 25 to 40 kilometers per second, the total trip time doesn't change. However, if we go high enough, after about 57, there is a drop in total trip time. And this because if the delta V is too low, although if we can reduce the transfer time to go to Mars, we have to stay on Mars longer, because we have to wait for the Earth to make one extra revolution around the Sun and wait for the planets to realign properly again. Instead, if the delta V is high enough, we can go to Mars fast enough and catch the Earth when it's still on time to do that. This study was about round-trip missions, because of course in the future they will become more common probably. Just think about the Mars sample return mission or future human exploration. In particular, rapid round-trip means a mission that is both short in duration and has a short stay time on the surface. If we focus on Mars, we can see that different kind of missions are possible, robotic or human. In the case of human, they can be exploration, colonization, commerce, or tourism, where of course the last ones are more far ahead in the future, maybe science fiction at this point, but still they can be applied to the study I made, so I still include it. If we could make a rapid round trip to Mars, the potential advantages of doing that would be the savings on the payload mass, life support system, operations and infrastructures, and reduced risk of exposure to zero-G radiation. The potential disadvantages would be the very high delta V required, and therefore the amount of propellant required. To do a round-trip mission in general, there are physical constraints that need to be respected. They actually must be respected. I list the 4 fundamental rules for round-trip missions, where the first one is the main one, so I'm just going to focus on that one. The difference in change in mission anomaly between the traveler and the home planet must be an integral number of orbits, which means must be a multiple of 360 degrees. This is a condition that must be met to have a round trip. Mathematically, this can be expressed with the formulas on the bottom, where we can see there is a term that has a W in it that represents the multiple of 360 degrees. That is the translation of the constraint. Now, W is an integer that can be either positive or negative. It's positive for outward trips and negative for inward trips. When W is equal to 0, we have a rapid round trip. And the next formulas represent the total trip time and the stay time on the surface. Now, these are the inner planet's orbit. T3 and T4 are tangential to the outer planet's orbit. T1 and T3 are direct transfers, and T2 and T4 are indirect transfers. Scenario F represents a more general case in which both departure and arrival are not tangential to the orbits. So where the flight path angle of departure and arrival can be any. And we also studied this case. Now once again, we're seeing the plot we saw before, but this time I added a new one on the right, which shows a T1, T4 round-trip mission profile, or what is generally known as an opposition class round-trip mission. And we can see that compared to the T1, T1 case on the left, the step reduction in total trip time occurs earlier at the lower delta V case. So this is a more appealing option, although the delta V's involved are extremely high. So they're clearly high, but they're lower than a T1 human mission applications, or at least it could be considered. For this 1000. Of course, to apply my calculations, I had to choose real opposition dates. I chose opposition dates in the near future, so we can think of near-term applications of this. Now, the synodic cycle of the planets, Earth and Mars, is made of 8 oppositions, which is equivalent to 7 synodic periods. And number 1 and number 5 represent 2 opposition dates in which the Earth and Mars are respectively closest to each other and farthest to each other. So I decided to study those 2 cases mostly because all the others fall in between. And we expect the 2018 case to be the most favorable in terms of transfer times and energy required, and the 2027 case to be the least favorable. The mission profiles that I considered for this case in particular are T1, 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 T4, and T1, T4, where T1, T4 is the non-tangent case, the most general case I showed you. This is one of many results that I obtained. There is a dissertation available in the paper if you need to see more cases, but this represents T1, T4 mission profile, where I'm showing you 3 different delta V cases. The green curve represents the lowest possible delta V case. The blue curve is a middle delta V case, and red one is the fastest possible delta V that maintains the transfer orbit and elliptical orbit. We could go, of course, higher than this, and the transfer would become hyperbolic, but we didn't study the hyperbolic cases at this time because there's already enough to learn from the elliptical ones, and the delta V's are already high enough. This plot shows once again the time versus the round trip delta V, and compares 3 cases. The black case is the assumption that the orbits of the Earth and Mars are circular and coplanar. Orange represents the case that includes the eccentricities of the orbits, but still assumes that they are coplanar. And the blue case is the real case, where the orbits have all the orbital parameters included. And this is just to show you the difference or the sensitivity in the results when we assume that the orbits are circular and coplanar, and instead when we include real parameters. For the 2018 opposition date, for example, which is the most favorable case, we see that the step reduction in total trip time occurs a little earlier than in the circular coplanar case. So the real case is actually more favorable. In 2027, instead, we have the opposite situation in which the step reduction in the actual trip occurs later, so a few kilometers per second later. So this is definitely a not favorable case. So what was done was, from here, after finishing the astrodynamical study, we took one particular mission and we developed it further. This is a T-1T4 profile, like the ones I just showed you, and we selected one case shown in the circles, in the green circles, which is right after the step. So this represents a rapid round trip case. Still at a relatively speaking, low delta V in heliocentric space. These are the parameters or specifications of the mission that I'm going to talk about. It's a T1, T4, which means direct, indirect transfer. W equals 0, therefore rapid round trip. The mission occurs in 2027, which is the most unfavorable case, so it's a sizing case. The stay time is 25 days. The total trip time is 1.11 years. You can see the transfer time durations. They're typical of a T1, T4 mission profile. And the closest approach to the sun is 0.528 astronomical units. Now this is clearly very close to the sun, and if we put humans on a spacecraft that close to the sun, of course we need to consider radiation, and we did this a little bit, although I have to say this problem is clearly still open. The problem of radiation is still an open issue, but if we wanna have a rapid round trip to Mars that doesn't take 2.5 years, just a little more than a year, I rather try to solve the radiation problem rather than giving up doing this. So even though the problem is still open, we should try to solve it at some point. This is the round trip mission profile. As you can see, on the top right, the solid triangle, the one more on the right, is the departure from Earth on a direct transfer to Mars. The triangles also represent the position of the Earth during the stay time on Mars, which means during the stay time for this mission, direct communication between Mars and the Earth would be possible. So it's actually